All right, let's dive into one of the absolute core questions in all of artificial intelligence. How in the world do you teach a machine to actually think? It turns out it all comes down to giving it a map of the problem and then a really smart strategy to find its way to the solution. Let's get right into it.
So just think about this for a second. How do you take a computer, which, really only understands code, and get it to solve something like a puzzle or a game or even figure out a maze? I mean, you can't just tell it what to do, right? You have to give it a framework for thinking.
And this very question, this is what takes us all the way back to the very beginning of AI research.
Way back then, the pioneers of AI, they weren't really thinking about things like chatbots or self-driving cars. Not at all. The big major research area was all about good old-fashioned problem solving. They just wanted to know if they could get a machine to tackle a problem the same way a human being does.
So they started with these classic games and puzzles, things you've probably played yourself. And the key they found, the thing that unlocked all of them, was this really powerful idea called state space search. Think of it as the engine that lets a machine reason its way through a problem.
Okay, so how does this whole thing work? Well, before an AI can even think about looking for a solution, it needs a super precise blueprint of the problem. You've got to lay it all out in a way the machine can actually understand.
The first piece of that blueprint is what we call the state, and it's exactly what it sounds like, a single snapshot in time. So for a game of chess, a state is the exact position of every single piece on the board at that one moment. For a puzzle, it's just the current arrangement of all the pieces. Simple as that.
Next up, you need actions. Now, these are basically the rules of the game. They're the set of all the legal moves you can make from any given state. You can't just move a puzzle piece wherever you want, right? You can only slide that blank tile into an open spot next to it. Those are your actions.
And finally, there's cost. This is just how we measure the effort it takes to make a move. For a lot of these simple puzzles, the cost for a single move is just 1, and the goal is almost always to find the path from the start to the end with the lowest possible total cost. We're looking for the most efficient solution.
Okay, I know these ideas can feel a little abstract, so let's make it super concrete. Let's apply all of this to a classic example, the 8 puzzle.
So here's the setup. You've got your start state, which is this jumbled up grid of numbers. And then you have your goal state, the perfectly ordered grid we're trying to get to. The AI's entire job is to figure out a sequence of legal moves to get from that messy start to that nice, clean goal. So sitting at that start state, the AI looks at its options. What can it do? Well, if it moves the blank tile up, boom, it creates a brand new board layout. If it moves it down instead, that's another layout. A move to the left, a third possibility. You see, each action creates a totally new state of the puzzle. And this right here is where the search really begins.
Now, this is where it gets really cool. Every single move creates a new branch. And then from each of those new states, even more branches are created. What you end up with is this massive, sprawling search tree of possibilities. The AI's job is to somehow navigate this huge tree to find the one single path that leads to the goal.
But how on earth does an AI explore a tree that big without getting lost forever? Well, it turns out there are 2 main ways to do it, and they are completely different from each other. On one side, you've got what's called uninformed or blind search. This is just pure brute force. The AI knows nothing special, just the start and the goal. It just checks every single path, one by one, until it stumbles across the solution. It'll get there for sure, but it can be incredibly slow. But on the other side, you have informed or smart search, and this is the game changer. It uses something called a heuristic, which is really just a fancy word for a clue or an educated guess, to help guide it towards the most promising paths.
And this is the perfect way to picture the difference. A blind search is like trying to solve a maze by just putting your hand on one wall and following it no matter what, even if it takes you down every single dead end. But an informed search, that's like having a compass that is always pointing you in the general direction of the exit. It helps you make much smarter choices at every single turn.
So why does this difference between searching blindly and searching smartly matter so much? Well, it all comes down to the absolutely mind-boggling scale of the problems we're trying to solve.
Let's go back to our little 8 puzzle. It's just a 3x3 grid, right? How many different ways do you think you could possibly arrange those 8 tiles? Take a guess. A few thousand? Maybe 100,000? Yeah, the numbers get crazy fast. Now, for the 8 puzzle itself,
There are a few 100,000 solvable arrangements, but the problem is, as soon as these puzzles get just a tiny bit bigger, say a 4x4 grid, the number of possibilities explodes into the trillions. It's just staggering.
Now, just try to imagine using a blind search to solve that, checking every single one of those possibilities one by one. The time it would take grows exponentially. It's not just slow, it becomes practically impossible.
So here's the critical takeaway. When you're dealing with numbers this big, brute force methods just don't work. They're not practical. And that's exactly why developing these smarter, informed search methods that use clues to make intelligent guesses, well, it's absolutely essential for solving any kind of complex problem.
So let's just tie this all together. State Space Search gives us the map of all the possibilities. But the real lesson here is that it's not just about finding any solution. It's about finding the best solution without having to check every single path. The map by itself isn't enough. The real magic, the real power, comes from the intelligent strategy we use to navigate it.
And that kind of leaves us with one last big thought. If a simple little puzzle can hide this much complexity, just imagine the real world. Think about a self-driving car trying to navigate a city, or an AI trying to plan global shipping routes. The number of possible states in those scenarios is practically infinite. And that, right there, is the grand challenge of modern AI, building ever smarter strategies to find the best possible path through a world of truly endless possibilities.